speaker, and who is going to talk about black hole superradiance. So if you can share your screen, please.
Yeah, let me start sharing my screen.
Yeah, now we can see it.
Can you see it full screen?
Yes.
Okay, perfect. So first of all, thank you very much to the organizers and to everyone in the audience thank you to the organizers for inviting me and for organizing this very interesting workshop. And thank you everyone in the audience for attending. So the talk I will be talking about will be about a specific classical process or well-known process in black hole physics known as black hole superradiance. And in particular, I will tell you a bit about also all these these very well-known effects can actually have possible implications for searches for physics beyond the standard model. This is essentially a connection that has been, there's been a lot of work in this subject in the last 10 years, and I've been involved in this work. So I hope at the end of the talk, we'll have a better idea of what exactly this is about. But before going there, let me remind you about some specific, properties of spinning black holes. And in particular is the fact that spinning black holes have this region outside the event horizon, where the dragging of frames is so strong that nothing can remain at rest with respect to distant observers. So this region known as the ergoregion stands outside the event horizon and allows you to think about thought experiments to actually extract energy from a black hole. And so a very nice picture of how you could do it. Imagine that you have, you attach a huge magnet around to some roads, and you descend these roads up to down to the ergoregion of a spinning black hole, because these roads are obliged by inside the region to co-rotate with the black hole. Essentially, these will turn the magnet over, and if you put some coils here that attach to, let's say, some huge light bulb, the time varying magnet that is induced by the rotation of the black hole generates a current and generates some turns the light on. And this of course happens because you are in the process, you're not extracting energy from nowhere, but you're actually extracting energy out of the available rotational energy from in the spinning black hole. And actually this process, as you know, has been, as you probably, most of you, I guess a lot of you know, in more formally has been the first time that, if I'm not wrong, the first time that such a process has been of energy extraction from a black hole has been thought about in a purely classical way, was by Roger Penrose. And essentially occurs due to the fact that inside the ergoregion, the conserved energy of a particle that you construct with the time killing vector can become negative inside the ergoregion, just because the time-like, also the asymptotically time-like killing vector becomes space-like inside the ergoregion. And if you think about a process where we initially sent in some particle with some given energy E naught, and this particle breaks up inside the region in such a way that part of it, let's say, gives rise to a particle that has a negative conserved energy, and another part flies away by conservation of energy, because the black hole absorbed then a negative energy. The piece that comes out of this process, E1, must be, of course, bigger than E naught, and this allows you to think about energy extraction from the black hole. And this led to all this historical way of thinking of extracting energy from black holes, led eventually to this famous process of black hole superradiance, through which you can extract energy by scattering basically the waves out of a black hole. In particular bosonic waves. So scalar fields or electromagnetic fields or even gravitational waves. And in the way this works, essentially imagine that you send a specific, so you send a monochromatic wave, so with some given frequency omega, and angular dependence such, that reads like this, where it is the azimuthal angle. And you're using the fact that the space-time is, is axisymmetric such that you can do this angular decomposition. And if the frequency of this wave is such that satisfies this relation where this capital omega is essentially the angular velocity at the event horizon, this process can give rise to also you can extract energy from the black hole. So the amplitude, so the energy of this wave that you measure back at infinity after the scattering process can be larger than the one that you initially sent in, and that happens at the expense of energy extraction, of energy and angular momentum, of extracting energy and angular momentum from the black hole. And in fact, although I'm talking specifically about black hole superradiance, there's been works in using analog systems. So, for example, a vortex, rotating vortex in a water tub, constructing an analog black hole. And this process of superradiance was actually for the first time observed very recently, back in 2017, for example, using these analog systems. There's also been some work observing these with sound waves. And so showing that actually it's a physical process happens, it's much more generic than just in black hole physics actually happens. The system is just a way to extract energy out of a rotating dissipative system. But for this talk, I will be particularly interested in the process that happens when you can have this energy extraction from a spinning black hole, which is this called the superrated instability, which is essentially a way to make a spinning black hole unstable because of superradiance. And the way that this can happen, if imagine that you have a test particle inside a test field that you scatter off a black hole, and besides that you put some giant mirror inside around this black hole, in a way that this mirror is completely reflects the waves that you scatter inside this cavity. And if some conditions are met, basically, because this wave will be superradiance-ified, if the superradiance condition is satisfied, after being reflected back, it can scatter again around the black hole, extract more energy from the black hole, and eventually lead to a cascade of energy extracting from the black hole, building up a field inside inside this cavity, and the system becomes unstable against. So the initial spinning black hole that you had put in here eventually spins down in the process until this condition stops to satisfy, for example. And this process happens exponentially. So it is a way to make a spinning black hole unstable against bosonic radiation. And there are several systems where this can happen. For example, a specific system is, for example, if you have an asymptotically anti-de Sitter spacetime, so where that works kind of an effective box. But also, perhaps more interesting in terms of astrophysics is the fact that it can happen if you have massive bosonic fields. And the reason is essentially because some massive bosonic fields, they naturally are able to naturally confine waves for which their frequency is smaller than their characteristic mass, or their mass in some units, where this mu essentially is the mass of the boson, scaled by the velocity of light and the Planck constant. So if you want 1 over mu is essentially the Compton wavelength of the Compton of the field. And so the way to see this, imagine that you're working in the perturbative regime. So you consider a test field that's on top of a spinning black hole. You consider let's say for simplicity here, a Klein-Gordon field, so a scalar field. And due to the symmetry of the space-time, you can separate your equation in terms of do separation of variables and separate the time and azimuthal part. And at the end of this calculation, you find out that the Klein-Gordon equation in a Kerr around the Kerr geometry can be written as this effective, let's say, effective wave equation, where with an effective potential is that essentially for a massive field asymptotes to a non-zero value at infinity, essentially asymptotes to the mass of the field. And this allows to create these potential wells around black holes, where you can actually form, let's say, quasi-bond states around black holes. And you can do the computation and compute, for example, the eigenvalues of this problem of this equation with given boundary conditions. So assuming that the field has to have ingoing radiation at the horizon and vanishes at infinity because you're interested in bound states. And the eigenvalues essentially are actually very similar to the hydrogen atom eigenvalues. So this part is actually, if you compute the frequency of this field of these eigenmodes, they're let's say the leading order in this alpha, where this alpha I forgot to put here, essentially this constant m times mu, which is, if you want, is essentially the ratio between the size of the black hole of the gravitational radius over the confine wavelength. So if this alpha is sufficiently small, you can write these eigenmodes in this form. So this is essentially equivalent to what you find in the hydrogen atom, plus some corrections that come from relativistic corrections. And more important, because you are considering a dissipative system that has ingoing waves at the horizon, the imaginary part of these frequencies have an imaginary part related to dissipation that can actually be positive or negative depending exactly on whether you are in the superradiant region or not. So if omega is smaller than the frequency of this real part of the frequency is smaller than m times the angular velocity of the black hole, which is exactly the superradiant, the regime where you can have superradiance, this imaginary part can be positive. And if you plug in this expression for the scalar field, you see that this field grows exponentially in time. So you have an instability. The system is unstable. So the Kerr black hole can actually be unstable in the presence of massive bosons. So this is something known for decades. And if you plug in numbers to know whether this could be interesting actually in nature, first you see that, so if you consider, for example, a scalar field, depending on the particular numbers, on the spin and the mass of the black hole and on this coupling constant, you get that this instability can be actually quite short on astrophysical scales. For example, using these numbers, you get 30 days, which are a very short time in the astrophysical sense. And if you consider, for example, also massive vector fields, and you could even also consider massive spin to fields, you get even smaller instability timescales. And the catch here is that this is especially interesting when when the ratio between the size of the black hole and the confine wavelength is of order 1 or 0.1 or further, let's say, unity. And if you plug in numbers in here, for example, if you consider, let's say, a astrophysically interesting black hole, so a 10 solar mass black hole, you will see that this is only interesting for very, very light particles, so for 10 to the minus 12 electron volts. And if you consider, for example, you discard primarily the black hole, so you consider, let's say, black holes formed from astrophysically some stellar collapse or from supermassive black holes. So these mass will range between, let's say, 10 solar mass up to 10 to the 10 solar masses. This will mean that these could only be interesting for particles that range from 10 to the minus 11, from 10 to the minus 20 electron volts up to 10 to minus 11, 10 electron volts roughly. And as you probably know, there's no particle in the standard model that that have this mass. However, there's been several proposals to that especially motivated either by dark matter or by low energy compactification of the interior, where we could have these very light fields. And this provides a way to possibly look for signatures from extremely light fields. But before going there, you need to understand exactly how this stability develops over time to know exactly the type of signatures that you will expect from this process. So as I said, the superradiance, essentially the process of superradiance basically extracts energy from a black hole. And if you have a black hole that initially has some mass m, mi, and angular momentum j, and you have just a small fluctuation of this bosonic field, ultralight bosonic field around this black hole, because this field, because this field is unstable around this black hole, it could be just quantum fluctuation or vacuum fluctuations. It will necessarily make the spinning black hole unstable if the spin of the black hole is such that the field becomes superradiantly unstable, and this will happen on a time scale tau inst. And this process will basically continue up to until you extract so much spin that you stop satisfying this condition, and at some point basically you form a field, let's call it a condensate around this black hole that is essentially co-rotating with the black. And because if you consider real fields on top of that, so fields that single field, because if you look in the stress energy tensor and if you plug in these ansatz in the stress energy tensor, what you have is essentially a time varying scalar field or vector field or whatever around it, and that is not axially symmetric, and so it necessarily generates gravitational waves. And this happens on much longer time scales. You can compute those through perturbation theory, for example, or numerical simulation that has also been done. And this gravitational emission happens on much longer time scales than the instability time scale. And so essentially the process looks like, you form this cloud and then the cloud just dissipates through gravitational emission, and the frequency of these waves are essentially related to the mass of the field. For example, if you had a 10 to the minus 13 electron volt, the frequencies of these gravitational waves of this field, these very long-lived gravitational waves, will be around 50 hertz. So exactly, for example, in the band, in the LIGO band, and on even longer time scales, because you emit gravitational radiation, this field starts decreasing. The mass in the cloud there in this condensate starts decreasing. And in reality, because actually this instability can happen for any mode M. If, for example, initially you had a black hole that was, let's say, in the black hole spin, black hole mass, in a black hole spin, black hole mass diagram, if you have the black hole that was in this position here, for example, it will be unstable in this case against L equal 2, M equal 2 modes. Well, the spin will decrease, and here these regions correspond to basically a region where this condition is satisfied, so it will stop to be unstable. And if you wait long enough, then it will become also unstable against higher modes. So in this case, M equal 3 modes. And at some point, it will stop to be affected by superradiance. In reality, if you could wait eternally, it will be unstable against all M modes. But because these black holes have finite lifetimes, for example, at most the age of universe, or less than that. During the lifetime of a given black hole, only a couple of these modes M can become unstable. And to give you some numbers, besides this, as I say, the instability times can be astrophysically relevant, but also the gravitational emission can be extremely long-lived. The time scale for gravitational emission can be extremely long. So for some given numbers where this here is basically the initial spin, so at the beginning of the instability, and this KF is the final. So it's the spin at the end of this process. So this time scale can be extremely long, so 10 to the 5 years. These, well, as you know, much longer than, for example, the merger of binary black holes that LIGO and Virgo have seen so far. So these are more like continuous monochromatic waves that will be always, almost always on during an observation, for example. Depending on whether you're talking about scalar fields or ultralight vector field, the time scales can be actually quite different. The time scale for vector fields, for example, will be much shorter, so it will be a different type of, and a much shorter signal, and this could, for example, allow to distinguish between different to actually distinguish between the spin of these particles if we ever detect such a signal. So that said, let me go through a couple of observables. So far I've talked about the process of this Superradiant instability, and I told you that it will be interesting to actually observe very light field, but of course that depends on for that we need to understand how actually you can observe this process. So a first basic process, of course, because we're talking about extracting energy from spinning black holes. You could just draw a diagram where you draw here the spin of the black hole. Here is I forgot to put the scale here, but this is the black hole mass. So here it corresponds to 10 to the minus 1 solar masses, and this here 10 to the roughly 10 to the 10 solar masses. So you could draw these diagrams, so these regions here, which would correspond to regions where any black hole inside this region, if there was a particle, for example, in this case, with 10 to the minus 10 electron volt inside existing in nature, and you'll have a black hole that is born inside this region, let's say, in principle, it will be unstable against the Superradiant instability, and so you should not observe at least black holes inside these regions. So these regions are basically drawn, assuming for a given mass of this field, you draw the contours for which the instability timescale is shorter in this case than typical accretion timescales that can have the opposite effect of increasing the spin of the black holes. And by observing, by measuring the spin of black holes and their mass, you can start putting points in these diagrams and basically tell whether a field with a certain mass can exist in nature or not. Just to tell you that, so these are, for example, signals X1 already kind of throws out scalar fields with around 10 to the minus 12 electron volts, for example, just from this simple fact. And actually there's been this work where they looked into the observations, so the spin measurements from the overall spin, population spin measurements, put everything together from the full catalog of binary black hole observed by LIGO, and they already exclude a region, which is basically this small region, this gray region, where it's basically the fact that you see some black holes, so it's actually only two binary black holes for which you can measure a bit the spin of the initial of the merging black holes. Fine, and you know that there must be at least one of them highly spinning. So from this fact you can exclude a particular range of boson masses from the fact that you see these black holes. And so in principle you could do by observing black holes from through the whole astrophysical spectrum from 10 to the, let's say, 10 solar masses up to 10 to the 10 solar mass, you could populate this whole region and either rule out the existence of particles with such masses, or on the contrary, if you will see patterns where black holes, highly spinning black holes, basically don't exist, you can in principle detect or find DINs for existence of ultralight bosons. Of course, if you are able to form these these condensates around spinning black holes, and imagine that you have a binary system. So you imagine a case where you have a bigger black hole that forms this cloud, and you have a smaller one that doesn't form this cloud, but the cloud condensate could be in both, but let's consider this simpler case. And these two black holes are in a binary. Of course, if you have the gravitational waveform that is emitted by this binary must be different from the case where you have a simple binary black hole just in vacuum. And there's been a lot of work in this subject. I'm not going to through all of them because there's way too much work for a small talk. but specific effect that can happen. For example, you can have dynamical friction just because you have a particle. So you have this particle in a non-vacuum environment. You can have resonances that can happen at specific frequencies where you can, excite in the same way that you can excite the modes of a hydrogen atom by putting, shining a light on it here by using a binary that at some specific frequencies you can excite some of these modes, and you can have resonance. If you have these huge environment, you can have tidal effects. For example, unlike vacuum black holes, if you have this condensate around it, the love numbers, for example, will be non-zero. The quadrupole moment of these black holes, for example, that you will measure in gravitational waves will be different than zero, for example, or will be different from the case of a single spinning black hole in vacuum, and actually could be quite large because you have this huge condensate around the black hole. And you could have also extremely very peculiar effects in, for example, extreme mass ratio in spirals. For example, it was shown by a couple of people that you could even have floating orbits in some specific frequencies around for indicate extreme mass ratio spirals. And we actually saw a couple of years ago, we looked into the case of, in a very simplistic, using very simplistic approximations, so using post-Newtonian approximations, we considered the case where you have an extreme mass ratio spiral, so you have a very small black hole going around a much larger one, and we tried to understand, in which range of boson masses LISA, the space, the planned space-based gravitational detector will be able to detect the dephasing due to the presence of this cloud there. If you have this field around the dephasing in the gravitational wave. I will not explain the whole detail of this computation. It is just to show you that there are particular ranges of boson masses for which LISA will be able to basically say, which correspond basically to this white region. Will basically be able, in principle, to say whether you will have a bosonic condensate around it or not. And actually, there's regions where you could do model selection, compare whether you have a cloud or something else. You could compare, for example, with other types of dark matter environments, for example, and this corresponds to basically everything above this line here. And so essentially, you could measure the presence of the cloud by looking at the gravitational signal emitted by a black hole binary. But the other aspect that I'm actually I wanted to spend a bit more time is this is the fact that you can actually this cloud itself, besides, is also an emitter of gravitational waves, and actually a very strong one. And so there's been a lot of work in the past couple of years to try to understand whether the monochromatic long-lived wave that will be emitted by this cloud could be actually detectable by current and future gravitational detectors. In particular, so in this plot I'm showing you, for example, the signal to noise ratio that you will measure, imagining that you put you have some given black hole that was born with 0.9 for some discoupling constant, and you do observation for 4 years, for example, and you basically plot the distance or the redshift, cosmological redshift of this source, and these plots basically are showing you the signal to noise ratio as a function of the redshift, of the cosmological redshift, and of the black hole mass. Because I'm fixing this value m times mu, a given black hole mass corresponds to a given mass for this boson. So, for example, LIGO is still basically only sensitive to corresponds to basically this gray region that you almost don't see here, because it basically only sensitive mostly to a possible source that will be within our own galaxy. While if you go to future generation of telescopes, like of gravitational wave observers, like the Einstein telescope, or even LISA, you could observe to much larger distance. And for example, for vector fields, you could even observe these gravitational wave sources up to basically to well, extremely large redshift depending on the mass, and you could basically observe any source that is up there if it's emitting this type of gravitational waves. And because of this fact, because you can actually observe, in principle, observe these gravitational waves, with current data, you can actually already say something about whether you have this type of field in the universe or not. For example, just in the Milky Way, you expect to have around 10 to the 8 black holes, and if you consider some astrophysical models and you consider what you would expect from the overall expectation of the emission of the number of let's say detectable signals that you should see given these expected number of black holes in the Milky Way, you can by doing what are called all sky blind searches, so essentially looking in the whole sky without specific in the specific regions, and which is something that LIGO already does for continuous gravitational waves. And you compute, for example, from given astrophysical models, the number of detectable signals that you would expect if given fields of given mass of bosonic field of inner mass would exist in nature. For example, imagine that you would have a field with 10 to the minus 12 electron volts, depending on your astrophysical model. So all these points are different astrophysical models. I don't have time to go through all of these, but essentially, in some models, you would have expected to already have detected, tens or hundreds of signals coming from these fields, from these sources. And the fact that you haven't seen anything already can be used to say something about the fact that you within some uncertainties, especially coming from the astrophysical models that you use to constrain the existence of bosonic fields in a given mass range. And besides that, so here I'm talking about the case where you can actually resolve one by one these gravitational waves. You also, the fact that besides these ones that you can resolve, there's many more in many unresolved sources in the universe, and these produce basically essentially a stochastic background, so a noise in your detectors. And so a couple of years ago, we did this computation of computing the stochastic background that will be emitted by all the sources in the universe, and we found that for some particular mass range, depending on exactly the astrophysical model and this that we use, these could produce extremely large stochastic backgrounds. And there's been already, results looking at LIGO and Virgo data to try to see if such a stochastic background, for example, is in the LIGO data. And LIGO hasn't detected any stochastic background so far, and this actually allows you to constrain also regions of the existence of boson, mostly in this range for LIGO between 10 to the minus 13 and 10 to the minus 12 electron volts. So that said, so this will, I went quite fast here, but the main point that I want you to take from this talk essentially is that black hole superradiance, because of the fact that it can lead to this black hole superradiance instability, provides actually a portal to search for ultralight particles in a very specific region of the parameter space. If you consider particles that exist between, let's say, the particles between 10 to the minus 30 until the Planck scale, it allows you to search basically in a scale which is around 10 to the minus 20 and 10 to the minus 10 electron volts. It allows you to search for these particles. And besides that, because it's a purely gravitational effect, it doesn't depend on the fact that this particle interact with standard model particles. So, for example, if these particles don't interact at all or very weakly with standard model particles, particle colliders will be completely blind to these particles, and essentially this provides a complementary way to search for these particles in a range that actually in some cases has been proposed as good dark matter candidates. And to finish, I want to just to pinpoint that in this last year we wrote this second version of this review on black hole superradiance, and we put a table there about the different constraints that are coming, that have been put over the years due to these different observables, some of these different observables that I talked about. And so we hope to keep this table updated, continuing to put the constraints that you can get from superradiance to constraints on ultralight particles. And I'll finish here. Thank you very much.
Thank you for the nice talk. So we have some time for questions. Let's see if there are some. Okay, it seems there is one question.
Yes. What is the key? Yeah, I was reading it. Sorry. Oh, yeah. The chi parameter. Yeah. So there was this question: what is the chi parameter that is used on several of your slides? I forgot to mention that. Thank you for reminding me. It's essentially the dimensionless spin. So essentially is the spin, the black hole spin, the dimensionless one. So the angular momentum over m squared. That's essentially, sorry about not mentioning it. Yeah.
Any other questions? Okay, there's another one from Shinji Mukohiyama.
Yes. Thank you for the very nice talk. So I think you mentioned that spin one field is easier to observe than spin 0. How about the spin 2?
Yeah, so I didn't mention here because, well, it's technically also more difficult and there's some, but I myself, for example, have done some work on the subject, but I would say the full problem is still not solved. So I've done the case where either you consider where either consider perturbational massive spin 2 fields on slowly rotating black holes, and we also did the case where we considered the case where you can what's called the Newtonian approximation, where this m times mu, so this parameter here is very small. So the full problem is actually not completely solved, because essentially so far there's been no way, there's no known way to separate the massive spin 2 equations on a Kerr background, which makes the problem more difficult to handle. But there's
Also, do you expect the difference between the massive gravity case and the bi-gravity case? So massive gravity case is, the background is produced by massive gravity, and we consider perturbation. On the other hand, the bi-gravity case, depending on the parameter, the background may be mainly from, to be precise, both of them participate, and then we consider both massless and the massive spin 2 on top of it. Do we expect a difference?
Right. Well, as far as I remember, the main difference between massive gravity and bi-gravity, if I remember correctly, is that in bi-gravity you have these two dynamical metrics, right?
Yeah, that's right. That's why we expect to have massless and massive.
Right. Yeah. I don't know, actually. I don't know what's the difference, because to be honest, I think especially, I haven't looked at that in some time, but I don't know, because it will depend really on the specific tier, I guess, because I guess there's nothing much is known about the dynamical behavior in those theories, as far as I know.
Okay.
So,
yeah, thank you.
Okay, so if there are no further questions, which I think that's the case, we're going to take a break for 5 minutes. Thank you very much for the very nice talk.